Okay, thanks everyone for coming. Good afternoon. Thanks for coming in on like a Thursday afternoon for our CASE seminar. So for those who might not be familiar with CASE, we're Center of AI for Society. We do a lot of research looking at how AI can potentially benefit and do truly social good type of work. Today, I'm truly honored and excited, glad to, my greatest pleasure to welcome Dr. Sadia Gabriel. Sadia Gabriel is assistant professor of computer science at UCLA. She's actually named for Forbes 30 under 30s a few years ago. Her work has received a lot of best papers, awards, and has been covered by a wide range of media outlets like Forbes, TechCrunch. She's, of course, also herself receiving a lot of research awards from major outlets such as Google and Amazon. Before coming to her current role, she was a faculty fellow at MIT, and then also she received her PhD from the University of Washington. Without further ado, let's give Dr. Sadia Gabriel a round of applause to welcome her talk.
Thank you so much for the nice introduction. I'm very excited to be here. So I'm going to talk about some research that's been going on within my group, looking at implications as we enter this era where AI has become so dominant and a major aspect of our everyday lives, and seeing where can this go wrong first, and then what do we do about it? How do we actually use AI as a tool to benefit society and to increase well-being of users? So over the past few years, we've seen this astonishing progress in strong computational models of language, we call large language models, and there's been a race amongst various tech companies to come up with stronger and stronger models that have capabilities to perform tasks. For example, being able to solve complex math problems, as well as in healthcare for drug discovery and mental health support. So we see a lot of therapy chatbots now, which have millions of users on an everyday basis. This all sounds very promising, but with this rise of very capable AI models, then we have to take into account what could be the risks, what could go wrong with this environment we now have. And some prominent figures within AI have pointed to these very real risks, including Gabriel pointing out if current trends continue, we will have AIs that are smarter than us in many ways, and they could skew our extension unless by that time we find a way to align or control them. So a less rosy picture of where this is all headed. We also see prominent figures in AI ethics and fairness pointing to some dangers of this dependence on AI. Margaret Mitchell saying the development of AI agents is a critical inflection point in artificial intelligence. While increased autonomy can offer genuine benefits in specific contexts, human judgment and contextual understanding remain essential, particularly for high-stakes decisions. And Gabriel pointing out that marginalized groups might experience misrepresentation if the technologies, large language models, become widespread in society. So this is a lot of talk that is concerning, but we're already seeing some of this manifest in a very concrete way. There's been a number of alarming failure cases over the last few years where we see misbehavior of AI systems that could hurt users. For example, one study showing that because of dialect bias that these large language models have, then if we're looking at criminal justice setting with agents, AI agents making decisions about who should be convicted for a crime or who should be given the death penalty, then they'll discriminate based on race. And we see speakers of African American English being more likely to be convicted by these large language models than other speakers for the same crime, and more likely to be given the death penalty. This is also true in other domains. So we had some work a few years back that was looking at content moderation, and we had this finding where we have an ironic situation that the very systems that are supposed to protect historically marginalized users discriminate against those users. And we see how these AI systems are not really taking context and information about communities into account when analyzing language. For example, when we have reclaimed language, which was generally held to be widely offensive, but then reclaimed within certain communities. So within that community, it took on a new meaning of a benign use. We see in this forthcoming work by my collaborator, Christina Chance at UCLA, that AI, these large language models, make similar decisions about reclaimed language as the outgroup outside of these communities, but very different, divergent decisions from the actual communities themselves. This is also a concern in healthcare. So here's an example of others' work in healthcare looking at how large language models will downplay women's health conditions versus men's when we have the exact same scenario. So we're looking at the exact same health scenario in these summaries, but we're just changing whether it's referring to a man versus referring to a woman, and it uses much more dismissive language when it's talking about the case where we have a female patient. This was a high-profile story that came out a few years back where we had a wellness chatbot, Tessa, that had to be taken offline because it was getting detrimental health advice to people with eating disorders and telling them that they need to watch their weight. And then also some work looking at issues of cultural insensitivity, where we see that these large language models and multimodal models, for example, vision and language models, will default to Western norms. So when we have a hand gesture, for example, that has a benign meaning in the US, but has an offensive meaning in another country like Vietnam, then it defaults to the US interpretation. So what do we do about this? Looking over all of these failure cases that have happened in the past few years, a lot of it comes down to a lack of understanding of the nuances of the context in which these models are deployed. So to really get an idea of how these models will perform in the wild when they're actually being interacted with by diverse users, then we need to take an interdisciplinary approach, I argue, where we are making sure that evaluation covers variations in value systems, cultural norms, and individual features of users and how they interact with these models. So to summarize that, then we need to have understanding of who the users are and what their expectations are. What are the distinctive features that differentiate different communities of users, like their shared beliefs, their linguistic patterns. And only then can we actually develop AI systems that are contextually grounded and safe for users to interact with. So as I go into this community-grounded approach, that's the overarching theme of the talk, then I'm going to start with defining what is a community in the first place. And when I'm talking about community here, I'm not thinking about a group of people necessarily in terms of a shared geographic location, but having some characteristics in common. So they might have similar shared history, shared beliefs. And there's been a lot of work, including I know some work here at USC on individual personalization. In this talk, I'm going to mostly focus on thinking about personalization for collective goals and alignment. I'm definitely not the first to bring this up. There's been a lot of prior work that has pointed out the need to center development of AI around specific cultural contexts. So there's been calls for situated studies where we have evaluation that's fitted to the users who within these individual communities who are actually interacting with systems. But we do need to be careful when we're thinking about trying to adapt to the value systems of specific communities and individual users. For example, we could think about a community of conspiracy theorists. So we need to also keep into account that there has to be some values that we hold for making sure that our systems are societally beneficial, so that we're not necessarily following what the norms are as set by, say, COVID-19 conspiracy theorists. And that point gets to the first work I'm going to bring up. So just to give a quick overview of where we're going to go with this talk, we're going to start off thinking about how we navigate biases of individual evaluators in determining the safety and overall performance of an AI system. For a long time, we've held human evaluation as a gold standard, but we're running into these cases where we have these very powerful systems that can outperform the evaluators. They might not have the background knowledge to actually reliably evaluate whether or not a system is performing correctly or whether it's safe. And they might, in fact, because of their own underlying biases and beliefs, lead to steering the system in the wrong direction. So we want to see, is there a way of assessing these systems when we have cognitively biased evaluators? And then in the second part of the talk, then we're going to start talking about what leads to large language models being reliable or unreliable reasoners in cases where we have weak supervision. We'll conclude the talk with discussing how do we actually come up with strategies for developing large language models that center community perspectives, and particularly perspectives of those who've been historically marginalized in a societally beneficial way, looking at a particular case study of mental health support. So I'll start with how do we assist cognitively biased users in assessing the reliability of systems. And this is work that was published last year at NeurOps with all of my wonderful collaborators shown here, and it is led by my PhD student, Salman. So the main goal of this work is to see how can we operationalize scalable oversight, which is this concept where we have a scenario of a very powerful AI system that has more knowledge than the humans who are evaluating it. So we can think of it in terms of this classic scenario where we have some human who has no coding experience, and they ask this very powerful AI system to produce a sorting algorithm, a code snippet for them. And then how do we actually determine if this is the correct solution that's been provided or not? So usually you thought of human evaluation in a case where we can find some experts that can do this task. But as we're going to the future and we're having AI complete more and more complex problems and forming these semi-autonomous systems, then that's not necessarily still going to be the case. And in fact, we already see lots of issues where evaluation hasn't caught very powerful capabilities of large language models to do harm. For example, seeing issues of large language models being used to create and spread disinformation and persuasion campaigns, manipulating elections. We also see there's been some high-profile cases of large language models leading young users to harm themselves. And then this example here that's shown from a CNN article was a case where a deepfake convinced a finance worker to pay out $25 million. So there's major implications for society if we don't have effective evaluation. One method we can think about for doing this type of evaluation that's been introduced in the past is debate. So this evaluation mechanism that was proposed was the idea that you have two different AI agents that are assigned to opposing sides of opposing opinions on the claim, whether it's true or whether it's false. And they have to argue with each other about which is the correct side to take. So we see them assigned to these two different answers, and there's different rounds to the debate so they can refute each other, as well as trying to make persuasive arguments for their side. And then ultimately we have a judge, the human evaluator, who determines which one of these agents came up with the better argument, which is likely to be the true label, the true answer for this claim. And there's some humanistic grounding for this kind of approach. So in human evolution, we've seen that argumentation is really critical as well. We don't gain knowledge through just sitting alone by ourselves. The way that we actually learn is through our interaction with environments, with each other, and being exposed to diverse arguments, diverse opinions. This is something that we've seen in a lot of the psychology literature. We've seen in work on human development with young children as well. And so here we're looking at how does this kind of adversarial AI debate work when we're trying to assess which one of these, we're trying to assess what should be the underlying truth in when considering a scientific claim. We also look at another kind of setting. So we look at consultancy, which is a simplified setting where we don't have this adversarial interaction between these two AI agents, but we only have one AI agent that's trying to convince the judge of a certain side. So they can interact over several rounds as before, and then the judge comes to a final conclusion. And the tasks that we look at in this case are factuality assessment tasks with different kinds of scientific claims around COVID-19, as well as climate change. And we selected these two specific data sets for a number of reasons. We had some selection criteria where we wanted to find cases where both the misinformation and the true claims seemed relatively plausible. We didn't want to have there be a stylistic tell, so we could shortcut making this decision. And there's a few other criteria that you can see up here. So for the judge recruitment, looking at human judges, then we ran this on Prolific, and we specifically selected judges so that they had varying beliefs, pre-existing beliefs around these two topics of COVID-19 and climate change. So one of the major takeaways, notable aspects of this work was that we're looking at cognitively biased judges. There have been previous work on the AI debate, but those were not considering the fact that there could be pre-existing beliefs that these judges hold that could sway their decisions. And so here we want to isolate that factor. And so we recruited equal numbers of judges who had mainstream beliefs that followed scientific consensus, say pro-COVID-19 vaccine, and then judges who had skeptical beliefs counter to scientific consensus, so say anti-COVID-19 vaccine. We also had diverse coverage in terms of demographics, looking at different ages, different education levels, origins in terms of where they come from, urban environments versus suburban environments, and so forth. So here we have some results looking at the effectiveness of these different protocols at this truth-seeking task, where we have debate versus consultancy. And we see that across these different settings where we have judges with particularly strong pre-existing beliefs versus they are more likely to be swayed, then debate is most effective as a protocol, though it does vary depending on the pre-existing beliefs that were held. So as we expect, it's going to be harder for us to actually change the beliefs of judges who have strong pre-existing positions, but we do see across the board an improvement in their accuracy in terms of actually being able to identify what is the ground truth label of these claims, whether they're true claims or misinformation claims. We also see here the kind of updates that are happening to the positions of these judges. So in the harmful update case, and that's when they initially had the correct answer, and then they switched after the interaction to the incorrect answer. So we see these harmful updates are more likely in the consultancy case than in the case where we have AI debate. And vice versa, we see more beneficial updates in the case where we have debate, particularly when we have judges who have low or moderate beliefs, strict beliefs. In the case where we have strong beliefs, then we actually see some improvement from consultancy. So now we're going to talk about what are the effects of the protocol design. So here we look at effects of what information is actually exposed to the debaters, as well as whether or not it's a human judge versus an LLM judge. And so I'll walk through these different settings that we have, where we have first the human judge results, and then we look at an LLM judge that has a persona. So these are LLM judges that are personified using information from our prolific study. So they're based off of the real human judges. And we also compare that against cases where we just have LLM judges without any human persona. And so public persona versus private persona is showing whether or not we expose information to the debaters about the background of the judge. And so we see the best case is actually having the LLM judge with a public persona, where we actually have better performance than a human judge. So this indicates that actually using these persona-based LLM judges might be an effective approach going to the future for doing scalable evaluation of whether these claims are misinformation or true. But is this generally the case that we can model users using large language models? And I'm just going to give away a spoiler that there are a number of issues with this. So no. And this work that we had at UNLP points out two of those issues that I'm going to address in the other studies in this talk. So this was some work that we had at UNLP that was looking into how can we use LLMs to model different users on social network platforms, and then trying to see if the behaviors of these LLM-based users actually matches the behavior of human users, and whether we can use this as a evaluation to predict the effectiveness of different misinformation prevention strategies, say. This was led by my student, Galen. So the way that we did this social network simulation is that we had a directed graph that's underlying it, and each of the nodes in this graph are LLM agents that are representing specific diverse users. And the edges within this graph are their relationships to each other. So who is following who within this simulated social network? We have different messages that get passed, as you would see in a real social network, and they can interact with this information in the same ways that humans interact with information on a social network. So they can share different posts with each other. They can like posts. They can flag posts based on whether or not they think that it might be misinformation. Here you can see what these simulated agent interactions look like. So it's a lot like a real X feed. And then we have how these individual agents are actually getting created. So we did a survey on Prolific as before, where we have this very fine-grained information about users, including typical demographic information, but also looking into some deeper information about what values do they hold, personality traits, what are their hobbies, to create as realistic LLM representations as possible. And so when we look at the behavior of these LLM agents, then there's a couple of issues that emerge. Problem one is that we see deceptive reasoning. So within this simulated social network, we have reflections where they can tell us why they completed a certain action. Why did you share that post? Why did you like that post? And when we examine these reflections, these verbalized reasoning traces, where they're explaining their actions, then we see that the reasons that they give for why they're doing the actions do not always match the action that they're completing. So, for example, you see most of the time there's negative sentiment for flagging posts. So we also see in 13.5% of the cases where they were flagging posts, we see positive reasoning, which seems counterintuitive and hints that maybe there's something that's not quite right here. Maybe they're not actually explaining exactly what they're doing, which is connected to this broader issue that we have within large language model reasoning of unfaithfulness, where the reasoning that's verbalized does not match what was the actual reasoning process that led to them making a certain decision, coming up with a certain output. Problem two that we observed from the study is lack of adequate user representation, particularly when we're thinking about historically marginalized groups. So we compared the actions being taken by these LLM agents against the actions being taken by real humans. We showed the agents and the humans the same social media feed, and we asked them to interact with this social media feed, and then we compared between the interactions that actual humans take in this social media feed snippet and the actions taken by their LLM agent representations. And so here we found when we initially look at it, then it actually looks pretty promising, where we don't see statistically significant differences most of the time in terms of their engagement behavior, the actions that they're taking when interacting with this social media feed. So there's similar behavior in terms of liking posts and commenting on posts. But we do see an issue where historically marginalized demographic groups are not represented as accurately. And this is something that's come up in other literature. This is just one work that I want to highlight here, a very nice paper where they pointed out that there's this issue where large language models, when they're steered to represent members of historically marginalized groups, tend to default to stereotypes, and there's less accuracy in terms of actually modeling behavior. So I laid out these two problems. In the next two parts, I'm going to discuss how we deal with these issues. So it may seem very bleak at this stage, but we actually have done some work looking into some solutions for dealing with it so that we can still use AI in a societally beneficial way. And so for the first problem, where we have this deceptive reasoning, then we have this forthcoming paper looking into when can large language models actually learn to reason and what factors make them more or less reliable at reasoning. So this was motivated by the emergence of these large language models that are specifically adapted to tasks of reasoning over complex problems. There's been a few models proposed for this, including DeepSeek and OpenAI, eyes models, where we have specific adaptation done over these models to make them particularly good at solving, say, math word problems or coding problems. And so I'm going to provide some background on how do we actually adapt these large language models to reasoning. I know we have a diverse audience here, so this may be review for some people, but I want to just have a really simple overview of what are the actual stages of development for these kind of reasoning models. So we'll start with initial stages of large language model development where we have pre-training. So initially we'll have some large corpus of web data that these models are trained on, and that's where they learn the basic structure of language. They learn about word meanings, they accumulate some world knowledge, and they understand, or they learn to mimic human language. And so this pre-training can come from very many sources on the web. We have Wikipedia data, we're going to have some code examples, we'll have social media data. And then after that, we have post-training. So this is where we can fine-tune the model so that it's particularly good at aspects like instruction following and making sure that it understands what kind of output is expected given the format of a prompt, user query. We have improvement in ability to fit to human preferences and aspects of safety, and then also reasoning skills can be improved through this post-training stage. I also bring up a few different methods for this. So SFT, usually supervised fine tuning that covers instruction following. RLHF is associated with alignment with human preferences. So that stands for reinforcement learning with human feedback. And then most recently, we have RLVR, which is reinforcement learning with verifiable rewards. And that was introduced for improving reasoning skills. And so I'll go into reinforcement learning with verifiable rewards. So the basic the basic structure we have for RL and NLP setting, where we're training a large language model. We have this agent, and so that's going to be the large language model that we're updating. And then we're going to have some training data that has examples of user prompts, and then we're going to generate completions to these prompts, and we'll score how good these completions are based on, in a lot of the work in reinforcement learning, so RLHF, for example, we would have a reward model that's trained using some supervised data, so you'd have some information about actual human preferences that were collected from annotators. But in this particular setting of RLVR, then we do it a little bit differently. So we're going to have a verifier script. So the idea is that we're focusing here on problems we can automatically verify. Like if we have a math problem, then we'll just check if the answer that's output is a valid answer automatically. And if it's code that we're generating, then we have some interpreter that executes this and sees if the result is what we would expect from correct code. So in the RLVR setting, we're going to have a binary reward where it's 0 if this was incorrect as a solution, and 1 if it's a correct solution. And then we just use that reward as feedback to then update our LLM. So this is very simplified. This is a very oversimplified example of how RLVR works. But these are the basics that you'll need to know as we continue on with this talk. And so the way we actually update the model will depend a little bit on what's the particular training strategy that we're using. We're going to focus on one that's called GRPO. So group relative policy optimization. So RLVR has become very popular recently within the reasoning community. And there have been a number of papers that have pointed to some astonishing results around how effective this actually is and whether this generalizes across different settings. So we see some kind of bizarre findings, like this works with only one training example, or this can work even if you have no ground truth data. This works if you have spurious rewards. So we just have random signal that we're using in reinforcement learning, or if we're using model confidence. So this is interesting and makes it really unclear, like what is actually being learned and why by these large language models. One thing that we noted as we were looking over a lot of this previous literature was that most of it just focused on one model, say the Quinn model, and on one domain. So we see predominantly this covering math. So it's not really clear if this is true when we're looking at other domains, say, or across different model families. So that was the motivation here, is we want to really understand what's going on with RLVR, and when does it actually generalize when we have weak supervision. So we want to investigate this more comprehensively. So we look at multiple domains with various levels of pre-training exposure. So for math, we expect to have seen a lot of these examples in the pre-training data already for the underlying model before we do any kind of post-training. For science, moderate coverage, so we still likely to see a number of problems, but less so than math. And then graph problems, then very low exposure. And we also consider more than one model family, so we look at Quinn, but we also look at the llama models. And And so here are some initial results when we're looking at generalization from 8 training examples across these different model settings in the math domain. So what these graphs are showing, we have on the x-axis, we have the training steps. So this is showing how long we've been training the model. The y-axis shows what our overall training reward is. And we see what we call a saturation point. So saturation is talking about when we actually see the reward hit its max and it plateaus after that. And so if we're looking at llama, then we see this happens really fast. It seems like it's just memorizing the training data really quickly. Versus we see a much more gradual saturation for Quinn. So llama is in the red, Quinn is in the blue. And when we look at the benchmark performance as well, we see that the benchmark performance on these evaluation math problems is actually improving over time for Quinn, but it's not improving for llama. So this fast saturation is actually causing a problem where the model's not continuing to learn. And then out of domain, we can see the effects as well. So SCP, that's a science problem benchmark. And we see that in general, after the saturation point, that performance is degrading. And in particular, we have lower performance for llama versus Quinn. So this pattern holds when we look at other domains. We also look at science here, where we flip it. So now the out-of-domain benchmark is math. And we see again, llama has very fast saturation, more gradual saturation for Quinn, and then similar flat performance out of domain for llama versus having some improvement for Quinn. So why is this happening? That's what we looked into next, is trying to pinpoint exactly why this happens. What is the difference between these two models where we would see this behavior for Quinn and not for, we would see this fast saturation for llama. And so here we look at the graph domain. So this is where we have low pre-training exposure. And we see here that we get faster saturation for both models. So they're a little bit more equal when we're looking at this science or this graph domain case. And this is the first time we actually see, depending on the benchmark, some stronger performance for llama. So that indicates part of it might lie in the pre-training. Another point I want to bring up is diversity. So generally in work on reinforcement learning, it's emphasized the need for diversity to have better learning, diversity in terms of the model outputs. So when we're sampling during the training process, then we'll have multiple potential solutions that we're considering that we can get signal from. And we want to see a lot of different solutions proposed. But what we're finding is that this assumption is not always the case. So when we look at the diversity of these outputs, then we find that llama actually has higher diversity over time, but higher diversity doesn't seem to be helping it in terms of actually outperforming Quinn. So this seems counterintuitive given what's been known before. And this just explains how we actually calculate diversity. So when I say diversity in this case, and we're talking about Shannon diversity, where we're considering not just having multiple types of reasoning being used, different reasoning strategies, but also how well are each of those different reasoning strategies represented in these candidate outputs. So why is this the case? This doesn't seem to make sense given what we know from previous work on reinforcement learning. So why does more diversity not lead to better learning? And the answer is related to what I brought up earlier, where we have this problem of deceptive reasoning. So when we actually look at these sample solutions, the rollouts, then we see that a number of them actually don't support the final answer in terms of the reasoning. So the reasoning is unfaithful to what the final answer is. And we can examine that here. So we see that Quinn, even though it's less diverse in terms of its outputs, it has more faithful outputs. So what we actually need to focus on is not just diversity, but faithful diversity. And that's where Quinn wins, or has more cases of different reasoning strategies where they're actually supporting the answer. So to improve generalization, then we address the domain knowledge gap. So we saw that Quinn was actually trained on 1 trillion extra math tokens. And so we just continue the pre-training of llama so that we have more domain knowledge exposure. So that's CPT. And then we also look at trying to improve generalization through thinking SFT. So thinking SFT is when we have step-by-step reasoning traces to initially supervise the model. And so we see that when we apply these two methods to llama, we actually get more gradual saturation, and it improves the generalization. And it also improves reasoning faithfulness. So the key takeaways from this part of the talk are that ROVR with weak supervision alone is not necessarily reliable. There's a number of cases where this doesn't work. And two of the main failure modes are fast saturation and unfaithful reasoning. We can fix this through doing this continual pre-training and thinking SFT, allowing us to generalize even when we have very little training data. And this also highlights the importance to actually look at saturation dynamics and reasoning faithfulness when we're developing these models. So that covered problem 1. Now we have problem 2, which was the lack of adequate user representation. And this is the last part of the talk, where I'll be discussing how do we develop specialized models that can actually represent perspectives of heterogeneous communities and situational thinking. And I'm going to be focusing on this domain of healthcare, and I'll talk about some motivating work within healthcare on specialized large language models. So this was the previous work that I was involved in with my student Salman, where we were looking at LLMs, clinical LLMs deployed in the NYU hospital system. So there had been a Nature paper that we were not involved with that developed a clinical LM using a large database of medical notes from the NYU Langone hospital system. And what we found was, so the results from this original paper were really, really promising. It was a breakthrough paper where we see that the small effective for clinical decision support tasks like readmission prediction. But what we found when we were looking at these different locations within the same hospital system, say looking at Brooklyn versus Manhattan versus Long Island, was that this performance was not equal at these different sites. So we actually see much lower performance at certain hospitals for readmission prediction that indicate that we actually need very localized models to operate well at these different hospitals, even though they're quite close in terms of proximity. Another motivating work is a study I did within mental health support that was looking at how we need to consider fairness and evaluation of mental health support tools, specifically looking at chatbots for automated psychotherapy. So if you look at a lot of the existing work on chatbots, in this case, like the Wobot paper, then they do human evaluation, but it's very skewed in terms of who the actual participants are in their evaluation. We see mostly white identifying patients. So there's a claim that this is generalizable, but we don't actually have the evidence to back that up. And what I found looking at LLMs deployed in this case was that there could be lower empathy for minority identifying patients like Black patients. And so that brings us to this current work where we look at how can we actually make LLMs better as being therapy support tools. So we're not thinking about completely replacing human therapists, but we have millions of people who need mental health support. In fact, 1.1 billion people are affected by mental health disorders worldwide. And it's been reported by OpenAI that 1 million users discuss suicide with ChatGPT every week. A lot of people are already using LLMs that have no kind of adaptation for therapy, and we don't really have regulation. There's also a lot of social pressures that might push people to rely on LLMs as therapy replacements. And there's a number of reasons why this would be more accessible to people who need therapy. We have a shortage of actual trained therapists, and we also, given the demand, and we also have very high costs for therapy, typically. So there is a gap here that people have already tried to fill with LLM-based chatbots. And there was this first study that was doing a randomized controlled trial of LLM therapists that was showing that there was comparable therapeutic alliance to human therapists. So there's some promising evidence for this direction with clinical validation. But there's a lot of reason why, in general purpose LLMs fail for therapy. And one big reason I want to highlight is the way that they're trained. So we already went over this post-training phase that they go through. I brought up RLHF, which is supposed to make sure that they're aligned with human preferences. But if you look at the data that is used for RLHF, then it doesn't cover domains that are directly relevant to therapy. We see coding, we see writing, we see general Q&A, but that's not necessarily generalizable to therapy. And we see misbehavior happening after this post-training stage that can actually harm patients, like encouraging LMs to agree with patients that could then lead to validation of self-harm. So in a therapeutic setting, we actually need clinically validated preference learning that takes into account therapeutic objectives like safety, empathy, patient autonomy, objectives that might actually sometimes contradict each other. Like, we want emotional validation, but we don't want it if it's going to cause harm. This is not something that we can capture just using a single criteria, single objective alignment. So we actually need to do multi-objective alignment that covers all of these different competing criteria. And so that's what we do, where we start with a lived experience survey. So we recruited participants who had experiences with mental health conditions from UCLA and from Prolific. And we specifically wanted to recruit a demographically diverse pool so that we can make sure that we're developing these models for all users. We did persona-based LMs based on the information that we have. So this is making sure that it's actually representing real backgrounds and value systems. And then we use this information to collect preference data. So we annotate our preference data to say which kinds of responses would be more therapeutically valid than others. And then we train our model on this preference data. So this shows some of what was covered by our survey, where we're looking at not just demographics, but their technological experience with AI, their attitudes towards AI and mental health, how do they rank different kinds of therapeutic criteria, and we end up with this information from 150 participants. We compare this against LLM specialized to general communication principles. So for this, we looked at prior work on cooperative communication and linguistics, Grice's maxioms that state that we should expect communication to be as informative as needed and no more, to be truthful, to be relevant, to be orderly and avoid ambiguity. So all of these seem important in any kind of conversational setting, but not necessarily specific to therapy. And then we compare this with domain-specific communication principles. So here we include the criteria that we surveyed patients on. So that was validated by prior work on psychotherapy. So we have a communication of understanding or relating to patients' experiences, encouraging patients' efforts to change, and supporting self-determination of patients. And so we can see how did patients actually rank this criteria, where overwhelmingly we see that empathy was a priority, but this alone doesn't tell the full story. So we also asked them to rate these criteria 1 to 5 in terms of their importance. And we see that even though there is one dominant leading criteria, then the ratings for all these criteria are pretty close to each other. So that highlights that we cannot just focus on empathy alone. It's important to consider other aspects like trust and rapport. So for actually training this model, this shows the baselines that we considered, where we have a model that's just Mistral model without any kind of therapeutic alignment. Then we also compared with GPT-4o, so we have a much larger proprietary model. We have the base model with some supervised fine-tuning focused on empathetic responses. And then we have our preference learning baseline. So this is a preference learning algorithm, direct preference optimization, that only focuses on one criteria, only focuses on empathy. And so DPO is like RLHF, but they took the reinforcement learning out of it. So it directly does preference optimization instead of creating a separate reward model. And then we have our multi-objective. I'm almost finished, I promise. Then we have our multi-objective settings. So we have DPO soup that looks at, we train models separately for each of the criteria, and then we merge them together into one model. And joint loss DPO looks at, what if we, yeah, I'll step through each of these. What if we just take the DPO objective, and then we do this for every single criteria. So we do it for preference data for all of our criteria, and we just sum this together in this objective here. This is the DPO objective. And then we have multi-objective DPO, which does this a bit differently. So we have a primary criteria, and then we have separate reward models for each of the auxiliary criteria. So I won't go through the details right now for the sake of time, but this shows some of the results from the study. So here we can see how each of these baselines and our multi-objective DPO model does on safety and empathy. So safety is on the x-axis, empathy is on the y-axis. And we see that by doing the multi-objective optimization, then we actually manage to consider both safety and empathy. So that significantly outperforms all the other models, including GPT-4o, which is a very much larger model. And this is all confirmed by statistical significance testing when we do pairwise comparisons, except for there isn't a significant difference between SFT versus GPT-4o on empathy, and then multi-objective DPO versus joint loss on safety. So this is looking at the general communication principles versus our therapeutic principles. So we compared using all of our therapeutic principles for a model versus using 4 of them against the general communication principles. And we do need therapeutic alignment. So that's shown here, where we see our best performing models with all the therapeutic criteria over just using the general communication principles, the Grexis-Massey model. And then we did a coalition validation study. So we had actual licensed clinicians from NYU take a look at these generated examples from our base model versus our therapeutically aligned model, and consider how well is one model doing versus the other on all of our criteria. And we see strong preferences by the clinicians for our adopted model across the board. And in general, we find that our clinicians agreed with the direction of the therapeutically aligned model. All right, so to conclude this and talk a little bit about where this is all going, then highlighted that developing AI for therapeutic use cases is not a general capability problem. We need this kind of specialization that actually takes into account domain expertise and the preferences of actual patients stakeholder preferences. Going into the future work, then we want to do more on this. So we're currently looking into having a multi-turn conversational setting with this model. And then there's also inference time techniques that we could use to improve the performance further. So we can look at retrieval augmented generation to incorporate more clinically validated information into the decisions and responses. So just wrapping up the talk, there's a few other works that I didn't get to go into that are related to this overarching mission of community grounded reasoning. There's some work we had at NLP that built on work by others, including Swaba, on looking at how annotator beliefs and their lived experiences impacts the way that they do content moderation. And so this was looking at how can we develop a new benchmark for toxicity detection that centers perspectives of annotators within marginalized communities, as well as looking at effects of context, conversational context on moderation decisions, and also work about to be presented at ACL 2026 by my student Sharif on developing resources for African NLP. So this was looking at trying to improve coverage of low resource African languages. And he led the student-driven effort, the African Languages Lab, to collect a vast corpus of speech and text data that covers 40 African languages. So thank you all. And that concludes my talk.
Any questions from the audience?
Yeah.
Thanks, Gabriel, for the great talk. I have two questions, both around the social media simulations, the agents modeling, different people on social media. One, did you, I think like your overall takeaway that agents model historically marginalized demographic groups less effectively. Were you like prompting each agent to like model a single human, or were you doing some sort of like distribution elicitation where you were trying to like elicit the distribution of responses for an overall subgroup? If you were doing the former, do you think that the latter could have better modeled these like marginalized subgroups? And the reason I ask that is from a recent position paper on language models can serve as, or simulations can be effective social science research methods.
Yeah.
The paper that I'm referring to there. They mentioned that maybe like distributional elicitation could be more effective in modeling marginalized subgroups.
Yeah, that's a great point, and I'm familiar with that work as well. So we were looking at an individual basis, and then our results were looking over the average from the individual cases. But that is something that we're interested in going into the future of seeing how do we have agents that are not operating on just an individual basis, but actually looking at them representing specific communities and in the aggregate. It's just, we have to be, it depends on the domain, of course, what the problem is, because one of the issues that comes up in this kind of work is that there can be significant disagreement just within communities themselves. And that's some of the work my collaborators are doing as well, as looking at when those differences occur. So I would say this is my answer to your question about the previous work with the individual level, but going into the future, we're definitely interested in looking at it on a distributional basis.
Got it. And just one more follow-up on that keynote. So were you prompting each agent with just like these socio-demographic characteristics, or were you also providing like examples of tweets, like real human tweets that someone with that particular persona may have said? Because I feel like in my experience when creating these sims, it's better to get the model to learn from more like latent features, the way that someone might speak, talk, instead of just directly prompting with demographics.
Yeah, another great point. So we looked at more demographics, but it was all explicit preferences and information. So we asked them things like giving a narrative about their background, or how did they decide to make friends with people, or what are their hobbies. So it was getting a little bit more personal, but it's not looking at their behavior. And there might be, you're exactly right, there might be behavioral patterns that emerge that they wouldn't explicitly state. And so that's another future direction.
Thank you.
All right. We are actually already over time, so if people have questions, please feel free to come after the class, after the talk, to chat with Sadia for a little bit, or you can also ask questions offline through emails. We have like our speakers contact here. And
Yes, I'm local, so please feel free to
it's
reach out.
local. And same for people online as well. With that, let's give Sadia another round of applause, and we'll conclude this